Okay, so we're going to talk about Docker. How many of you are familiar with Docker already? Probably quite a few hands there. Good. I see a few hands that didn't raise. You're either don't know about Docker or you're shy. But we're an open source project for containers, Linux containers primarily. Although we are looking at doing things like FreeBSD containers and so forth down the road as those opportunities present themselves. FreeBSD jails, for instance, work. We have over 400 contributors, 1,800 forks on GitHub, 10,000 stars on GitHub, dozens of projects built around Docker, using Docker, other startups that are building themselves around Docker or making it a core part of their business plan or part of their products, such as CoreOS and Orchard, and amongst various other companies that are finding it useful. Docker itself is about 40 to 50 employees. We have a Series B funding. And I've been at Docker since January. And before that, I've been, my name, by the way, is Windisch. And I've been doing OpenStack development for 4 years, which is an open source cloud computing platform. And before that, I owned my own ISP, hosting service called VPS Village, which basically looks something like Linode, but we were doing that in 2006. So I have a lot of experience in this space, and I'm going to try and help you ship your code. So Docker tries to solve this problem of shipping code. You have all these different applications. We call this our matrix from hell, where you need to have all these applications run on your laptops and different types of laptops, Mac OS, Linux, servers, large server farms, OpenStack deployments or cloud deployments. And it's this matrix from hell, right? Because what happens is your laptop or your developer environment sometimes looks like this shack on the water, where unless you're a very highly organized shop, a lot of times your developers are bootstrapping their own environments, and maybe those things are fairly standardized, you're using Vagrant or so forth, but everybody wants to customize it, and they're going to have their little specialized Vagrant environments or EC2 VMs, or maybe even just a directory on their file system where they edit their code. And not everybody's environment is the same, and sometimes the developer's environment looks like this, and sometimes it's a mansion on these same stilts in the middle of the ocean. And it's a problem because, first of all, you're repeating a lot of the same work. Your developers every developer is doing the same thing. And sometimes you help them by trying to share that environment, but not all of your developers are happy with it, and they're going to recreate the wheel. And the other thing is, many of your developers aren't infrastructure engineers. Their primary job is very often to develop code, not to build infrastructure. So that's why a lot of times it's kind of built on stilts. And it doesn't look anything like what you're actually deploying in production. So you build testing infrastructure, right? You build this complicated system where you can test things out, and it's flexible and maybe not scalable because it's just your testing infrastructure, but it can put your software through its paces, and it's fine, except it still doesn't look like your developer's environment, nor does it look like production. So your developers are still testing things locally on the shack on the water, and then they upload it into your testing infrastructure, meaning that your testing infrastructure now has to be really big to accommodate all the tests that your developers are now pushing onto it, sometimes waiting half an hour, 2 hours for tests to run in your centralized infrastructure because they couldn't run it on their laptops, or because they weren't, or you have to run it, or rather to say that sometimes developers will not catch a bug locally because their infrastructure wasn't really that great. And only this complicated full testing environment is going to discover it. And of course, this is what we're really deploying, right? We're building skyscrapers, and it's kind of like building circuses and carnivals in order to try and build this skyscraper. So there's something missing here, right? There's homogeny, this sameness. These systems are all different, whereas what we really need to do, this sea of sameness, this actually is not Levittown, PA. I originally had a Levittown, PA, which is where I grew up actually. And the idea was to have all these houses built the same because it reduces costs, it reduces complexity. And you can build a lot of them and they all look the same and you know what the problems are. And sometimes you have problems, but all the problems are the same and you can fix those problems en masse. Just like software should be, right? The Model T Ford, gun manufacturing, everything becomes standardized, mass-produced parts where you have this, where you get cheaper and faster iteration. And for shipping physical products, you had this intermodal shipping container, and you can get goods from China to the middle of the United States on this single unit. So they load this up in China, they put it on a ship, and then they'll take it off the ship, and they can put it on a train, and then they can get it off the train, and they can get it on a truck, and it's the same container the whole time. And you don't have to be repackaging it and rebundling it. So that's what Linux containers give for you, right? In theory. But Linux containers, LXC in particular, doesn't really do anything, right? Docker builds upon that because it's not just a containerization of the processes on your host, but it's a bundling of those things. It's like in Java where you have classes. You can compile your code in Java, and you can have a giant directory structure, and you can ship that, or you can put everything inside of a war, right? And you can share that war file and deploy that on your various systems. That's kind of what Docker does for containers. It allows you to have this standardized bundle where your application includes not just your code, but also a certain amount of infrastructure along with that, right? It combines your application and the system's requirements for that. So if you need a specialized Apache configuration, for instance, or an Nginx configuration, you can bundle that in with your application and make that part of your application and not just some really complicated document for how you're going to install this and deploy it. Which makes, of course, shipping your code to your consumers or your users a lot easier. And those can be internal customers, other teams, or they could be customers to whom you're shipping code. Over and above what we have for standard containers is it's open source, it's open, easy to use, where we have these Docker files, so you have easy image building. So you can basically create a recipe and define what you want your images and your containers to look like. It's portable and shareable, so you can take these containers and these images and share them to other people. We have there's a thing called a registry and an index, and you can share these either privately or publicly with other users or other teams. And what we have above, let's say LXC, is a completeness of vision. So we're not just looking at making a virtualization technology. We're looking at an ecosystem. We're looking at making this something that works in the cloud, cloud services, and around that, and so forth. So what we want to do is be able to deploy reliably and consistently. If it works locally, it will work on the server. It will work with exactly the same behavior, regardless of the versions in, say, your operating system and your dependencies, because you can build your dependencies into your application, regardless of distributions. Again, your image contains the distribution. So if you're, say, a rel shop and you have this application that only runs on Ubuntu, well, Ubuntu may be inside of that container, but as a rel shop, you actually don't really need to care about that because it's only one process. The only thing you're getting from, say, Ubuntu in the perspective of that application are the libraries that it imports. It's actually not a full generally is not a full system with an init and hundreds of processes on the host. It's just that process, and it uses the shared libraries that it may need to from the file system, which may be seeded from an Ubuntu image. And regardless of dependencies. And I shouldn't call Ubuntu out there, right? It can be the other way around. It can be an Ubuntu host running RHEL inside of containers. So it runs everywhere as long as everywhere is Linux. And you need kernel 3.8 or higher. With the exception of RHEL 6, there's a backport for all the Linux namespace requirements. So containers are just like the real thing. They're just like real hardware. They're just like VMs. In fact, they're, in many ways they're like VMs, but they're not because the process is just on the host. But they're real things like other processes. They work in your development environment. You can run your services in your containers. Whatever you want to run or test can run in those containers just like it runs in production. You can build those images instantly or in seconds. Or hours, depending on how complicated your Docker file image building process is, and you can run them instantly. It's fast. They're lightweight. Laptops can run tens or hundreds of containers easily. Servers can run tens or thousands of containers. Containers run at native speeds. So they're not like VMs. You have this layer where you have to certain system calls will have to generate interrupts that get caught by the CPU or by a pair of virtualization layer, and it's going to basically cause an exception, and that's going to basically rewrite that system call to run in the hypervised environment. It's a fairly slow process, and there are things like IOvert and so forth that fix this or improve it, but containers are just other Linux processes on your host. Just like any other process that you run on your Linux machine, these Linux containers are just processes. And in fact, they're not even processes under another process necessarily. They just are, when you launch this process, it happens to be contained, well, it happens to have a certain security restriction on it. Just like, say, running SE Linux, Linux namespaces basically say that this process can or cannot access these various things. And primarily, any performance decrease that you see is just your kernel checking, am I allowed to access this file? Which, by the way, your kernel already does when it accesses files, right? It will say, can I access this network? OK, well, Linux doesn't normally do that, right? But that's a good thing from a security perspective. Right now, you can say, I want my application not to be able to access that whole site subnet. That's a good thing. And it's not any worse than any other DAC type constraints that your OS might have. So this is going to be a bit of a small case study where this is a Docker image that I built called DockenStack. And what I wanted to do was run OpenStack inside of a Docker container. And it's a single Docker container. It's not the typical way that you would build Docker containers. Normally, you'd want to try and put one service per container. This is many, many services in one container. But the reason I did this is because I'm trying to test the whole homogeneous system, and I'm just trying to do code testing. I'm not trying to do environment testing. This isn't for production. This is to replace a Vagrant-based system. And what we were doing was we would use Vagrant on your host, and it would create a Vagrant VM, which ran Linux, and then spawned a bunch of VMs inside of it. But I don't like nested virtualization. It's kind of slow. And there are also a number of other reasons I'll get into in a moment why Docker provided a great advantage for us. But quickly, by using Docker, we were able to then remove the nested virtualization, right? Because here, primarily, what we were trying to do was have a repeatable, testable environment. We didn't need or want a VM. We just wanted a way of combining all of those processes and not infecting our host. Because when you run OpenStack in a testing environment, you're talking about bringing up MySQL, RabbitMQ, maybe 20 or 30 different services for OpenStack itself. It changes your network configuration of your host, including your ETH0 interface. It does a lot of really nasty things that you really don't want to be doing on your machine. In fact, the documentation says do not run this on your laptop. Run this in a VM, run this on the cloud. So I put it in a container because I didn't need VMs. The other reason is because like many other things like Chef or Puppet, this particular devstack, which we use for OpenStack, basically is a recipe, right? And like any other recipe, when let's say you use Chef, you have this recipe, but it has all these ingredients. And these ingredients are things like flour, salt, those are easy ones, milk, cheese, chicken flour, okay, butter, chopped onions. So the problem is, what happens when you don't have the ingredients that you need, right? Now, in a CI, that's a problem. Like, companies stand up things like app caches, RPM caches, sometimes even their own DNS servers, whatever network resources that you need in order to get your application running in CI. Very often, if you have a complicated system anyway, you're downloading them and pulling them in every time you run them. At least it wasn't the case of OpenStack. So it would take over an hour to, when you ran a Vagrant VM, it would take an hour from launching it to actually OpenStack running, because I had to download all these things and then install them. And it took obviously it took a long time. And the worst thing was that if the PyPI servers were down, or if you're a Ruby developer, it might be the gem server, but we were using Python, so it was PyPI. And if the server was down, you might be half an hour in, 45 minutes in, you get an error connecting to the server, and now your test is invalidated, and you have to restart it and hope that maybe PyPI is back. And so if you're in a professional kitchen, right, they have all the ingredients. They get all these ingredients all the time. And like I said, if you have a really good CI system and a Jenkins setup, you might mirror these things. And you're going to make sure all those ingredients are readily available to you. What's great about using Docker for this, in this case, was that I could build a Docker image that already had all these network resources. The only thing I was loading every time I ran a test was my own code. So I would do all the PyPI downloads and setup beforehand in the image, but then for the sake of what happened if somebody updated PyPI, when I ran the image, I would just check and see if there were actually anything new that I had to download. But if it failed, I didn't really care because I already had something installed. I may not have something from the last 12 hours. I might have a PyPI requirement that is 12 hours old. God forbid. Right? So anything that's network dependent that might cause false positives is usually eliminated by doing that. And again, when you have developer laptops that want to be able to do this testing environment, you have this advantage of not having to have that giant infrastructure around it. Everything can be on your laptop. Okay. So Docker is kind of like the bento box. And what I like about bento boxes is that they're suitable for serving in a restaurant. You can make them at home, but they're also not that different from a TV dinner, right? You can kind of freeze it and image it, and it works in all the places. And what you could do here, as I was explaining, is you could basically make a bento box, freeze it, but maybe not have that lower right-hand corner. Maybe take that orange out of there, and maybe your code is that orange. And when you run your test, you just insert it in there, and then you can kind of taste the meal, I suppose, as you want to if you're doing CI. So what we do for Docker and Stack is we install all the pip requirements, check out all the Git repositories. All the Ubuntu packages are either installed or downloaded. Some of the packages, basically, you can't run them during the build or install them during a build, so we run them during the run, and we freshen them. So Docker uses a bit of a shift here. Slide was out of place. We use copy and write for quick provisioning of images. We can create and share those images. We have a standard format, and they're reproducible. All right, so we're going to get into some of the nitty-gritties of how Docker works. And this is mostly about namespaces. Yes, you can call Docker a lightweight VM. You can use it that way. It's not the only way to use Docker. But from the perspective of a lightweight VM, you get your own process space, your own network interface. You can run things as root. You can have your own sbin init, but that's not normally how people use Docker. There are use cases where you want to have that, especially if you're, say, importing a physical machine that you already have and you're doing a sort of like a VM-style migration strategy. And there is actually a project out there that basically, somebody created a Docker file, I think called Fusion Base Image, which is basically built around that concept of having, here's a Docker file that has an sbin init, and it makes it easy for you to port your apps that already run on Ubuntu, and you can have SSH into containers and so forth. Right? But then the other direction is it's chroot and steroids. You can not have the sbin init. Container is just an isolated process, maybe a couple processes. You share a kernel with the host, so you don't have this full virtualization. If there's a kernel vulnerability, yes, you have to worry about it because it affects your container and the host equally. And there is, through the kernel vulnerabilities, breakout potential. No device emulation, which makes it faster. We do this with namespaces. A lot of namespaces are a relatively new kernel feature. I'm not sure exactly how new, last 2 or 3 years, maybe 3, maybe even 4 years now for some of these. The user namespace, I think, has only been there for 1.5 years, 2 years. And what these do is they allow these processes to see a different number or a subset of the processes in, say, the case of the PID namespace. When you have a container running or a process running inside of a PID namespace, you can only see your own processes. So on the top, you're running on the host, and you have 212 processes, PIDs, on the system. But then on the lower, on the second line there, you do psaux, and you can see you're running bash, which was the command you're running in Docker. And then you did psaux, which is, of course, your second process. Normally, when you run a Docker container, it's going to launch one parent process, and then that can potentially spawn other processes, such as psaux. You have a mount namespace, so you can see a different set of mounts. And again, on the bottom half here is your Docker container, and you have 10 mounts. The reason we have 10 mounts in that Docker container is that they use cgroups. So the cgroups are apparent as mounts, and they'll list in proc mounts or in the mount command. You have a net namespace where you get your own set of IP addresses. I think Docker uses 172.17 by default. It's kind of hard-coded, but you can change it. There is now, in Docker 0.10, I believe, pluggable networking. So you'll be able to actually, people will be able to create networking plugins where you can modify and change how the networking occurs. There's a UTC namespace, meaning that you can have your own host name. So you go into a container and it sees its host name as being something different than the host that it's running on. But it's the same host, it's the same kernel. It's a different, if you can actually go on the host side and you can do a psaux and you could see root on the bottom half running host name on that machine. But what that host name process sees on the bottom half thinks its host name is different. You have IPC namespace, and you get different shared memory segments and sockets. User namespaces, you can have different multiple PID zeros, UID zeros. So you can basically have processes that run as root, but are not root. So as those processes understand they are root, but they're actually not executing as root on the host. It's kind of meta. It's hard to explain how that works, but basically as far as the process knows, it's root, and it can do anything root can do, with some exceptions. It can't generally mount file systems. It can't write to dev, kmem, and so forth. There's actually a way in Docker to make allow containers to do those things, but by default they're actually disabled by a security policy that has actually very little to do with the fact that it's is or isn't root. Just like you can have, say, SE Linux capabilities that can make root not do things, you can use Linux capabilities to say this root user isn't allowed to actually mount file systems. We use isolation with cgroups. You can limit the memory, the CPU, the blkio, and devices that you can access. Memory as in how much memory the set of processes that you run can use, how much CPU shares you get, and so forth. You have a memory, okay, so I guess we dive it down into these. Memory cgroup keeps track of pages used by each group, what memory they can access, or what they're allowed to access, how many pages that they have, shared pages, and so forth. The out-of-memory killer, I think, may be separated as well. Okay, CPU, yeah, those weights, grouping, you can do pinning. Right, and it's kind of NUMA aware too, so if you have a NUMA system, you can care about that. Blkio keeps track of IOs for each block device, read-write, sync versus async, relative weights. Devices, what devices you can read, write, modify, or you can mknod. Generally, you can allow things like devtty, dev0, devrandom, devnull. We deny everything else by default. Again, there is an ability you can pass dash privilege to Docker, and it basically removes all the restrictions that your Docker container has. You can use dash privilege, for instance, to run Docker inside of Docker, because you basically running as root. It's actually fairly useful. For Docker and Stack, we actually use Docker and Docker, and we allow it to do much more than it probably should. Copy and write storage. So everything in Docker uses copy and write storage. So when you make a change to a inode on the file system, it actually writes to a new file system. It doesn't overwrite the current content. So we can do this via different file systems. You have union-based file systems such as AUFS. And you have, it says snapshotting file systems, but I prefer to actually call these copy and write file systems, but they're not copy and write block devices, which is another matter, right? So ZFS, which isn't mainline, but it's something I particularly enjoy and like. And what happens is when you write blocks, they write into a new file system effectively, or into, in case of ZFS, that actually keeps track of things a little differently than a union file system, but all that really matters to you is that these are copy and write devices, and you can always roll back to the last snapshot effectively. And you can commit an image and make a new image from the changes that you've made. So we're going to go a little bit over how to use Docker. And again, one of the great advantages of using Docker is that you have this thing called a Docker file. And this is a really simple example because it uses, I think, 4 commands, which is from Ubuntu. So we're going to start with a basic Ubuntu image, and this will be Ubuntu latest, which currently is precise because it uses the latest LTS. And I know that precise is not the latest LTS as of last week, but I don't think that we've updated the tag yet. So probably in the next, it may already be out. In fact, I may be speaking incorrectly, but very soon, if not already, that will be trusty. But right now, when I did this presentation, it was precise. And then it will run these commands, and each time it runs one of these commands, it makes a new image and uses the copy and write feature. So however many lines there are, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you basically get 11 images out of this. And when it finishes building and makes the final image, it'll usually delete all of the other intermediary images. But you can optionally keep them if you want to. And one of the great nice things about that is that if something fails, let's say make install. You do run cd apache couchdb configure make install. If that fails, if make install fails for some reason, it will actually exit at that point, and you can go into that image and inspect it. You can get logs from it. You can try and manually fix it, and you can kind of resume from there and then see, and basically debug your Docker file. And there's actually quite a few commands here, more above and beyond run. There's things like add, so you can add files. You can download files into here, extract tarballs. And then you build this with this command on the bottom, docker build. You give it a tag, but basically that's a name. So when it finishes, the very last command that runs, that image will actually get a name. Otherwise, it'll just have a SHA, which is only moderately useful, unless you have really good memory for numbers. So if you're moving to Docker, you normally want to have one service per container. You want to Dockerize, you'll Dockerize your service. You can containerize administrative functions such as logging. Ideally, you'd put things like syslog into its own container and do network logging. Perhaps now or in the future, you could even do logging over IPC into another container, so you could share the IPC namespace, for instance. Again, you want to try and split the services. You don't need to move everything to Docker. So you could say make a physical syslog server, do something more traditional IT and have an actual physical syslog server, but then have your containers talk to that physical service. There's no reason that everything immediately has to be on Docker. But you don't want to use containers as VMs. So ideally, you wouldn't give them a sysbin and a SSH, and then log into them, and then run chef, and then bring up all these services inside of it. Ideally, you'd actually orchestrate things on your host side and run every process in its own Docker container. And one of the reasons, again, is that look at it from a security perspective. Docker provides you a security story for separating and providing isolation between these processes. And if you put everything in the same security context, you're not getting a benefit from having security contexts, right? So this is just a little example of a multi-tiered application where we have a load balancer. We're bringing in BGP and OSPF at the top, and we're doing load balancing using ECMP and Quagga, and that's connected directly to HA proxy. So this is one, the top here might be a single image that has multiple processes. And while ideally you may not want to put Quagga and HA proxy together, there's no reason, in this case, it may be fine to do it because in this case, they're very tightly coupled, where Quagga is effectively Quagga is a routing daemon. So basically, Quagga would be announcing, hey, HA proxy is here. So it wouldn't make sense in this case to debundle them because the whole purpose of Quagga is for service discovery. So Quagga is just basically a service discovery daemon in this example, and it makes sense to bundle that in an image with HA proxy. Whereas image layer 2, you want Apache, your Nginx, your HTTP service. This is probably your actual application, your REST service. And this is going to be in a single container. But then MySQL or Zookeeper or whatever your database might be, CouchDB, would be in a separate image. And to kind of drive this a little further, I mean, if you really wanted to, you could maybe combine your HTTP service with something like Zookeeper in an image. Probably wouldn't recommend this, but there's no reason you couldn't, given that Zookeeper is distributed, and as long as you don't scale to too many HTTP services, and you keep at least 3, that you could do something like this. So when you're using Docker, you create these local builds. And when you're satisfied with it, you can push it to a registry. This, by the way, is how you get your code out there and you run it. You can run it locally. You can run it in your CI. You can run it in production. And it's that same image. And you can run this, when I say in production, but this can also be, this can be the cloud. This can be a local server. And it can be both. So if you're doing hybrid cloud, for instance, let's say you build a small little local cloud either for your testing or for your local use, or maybe you need something on a customer present site. It can be effectively the same environment and the same image, or rather the same image despite the fact that they're completely different environments. And when things go wrong, you can roll back. So you can just say, oh, well, I don't want to commit this image. I don't want to save it. I just want to toss it. And you can go back to an earlier version. So I'm a big OpenStack guy. So I'm going to talk just a moment about Heat, which is an orchestration service that's part of OpenStack. And this isn't specific to Heat. You can use things like Mesos and Cloud Foundry. I'm using Heat because I know it well. And with Heat, what we do is we have this orchestration service that allows you to specify resources. And these resources are not that different than something like a resource in Chef. Now, Heat is actually started as an implementation of CloudFormation. So anybody who's used CloudFormation, this is pretty much, we're talking about the same system by almost a different name. That happens to be open source. And we have a Docker resource. And you can say that you can create a resource and it's going to talk to a Docker daemon. But it's disconnected from the actual compute. So what you do is you talk to the cloud and you say, give me a VM. And you get the VM back. And then you talk to the VM and you say, I want to launch containers on that VM. And you would control this with a template that looks something like this, where you create an instance with OS Nova Server. There's also one for Rackspace, so you can actually run this theoretically locally and then launch onto Rackspace. And you could then specify your key, your image, the flavor that you want, say an M1 large. You specify user data, which is what's going to install Docker onto, let's say, a plain Ubuntu image. And then you say, I want a Docker container. And it's going to give you a Ceros, which is a small cloud image that will run. And you'll have this container running on that host. So now, not only do you have a VM, but now you have a VM that is running this Ceros image or the Ceros application. And what you can do is use this to orchestrate workloads across the cloud. And again, this type of pattern is supported on things like Mesos and Cloud Foundry as well. And unfortunately, I don't have examples for those, but I hope you can see how you can basically apply that to those different orchestration services. So, all right, we're going to do a small demo, and we have enough time. Good. So what we're going to first do is install Docker on EC2. That's all you have to do. That AMI, by the way, is the standard Ubuntu image, the official Ubuntu image. And we give it a key and we give it user data. So there's something called Cloud Init, and it basically takes user data and it knows how to interpret it to do something. And Cloud Init is a part installed by default with Ubuntu. So it understands that when you're running on EC2, if you give it something under user data, it's going to load this and knows how to parse it. And in this case, we're installing Docker. So we run that EC2 image, and we're basically just going to SSH into it. All right. Then we can run Docker. Now, what happens when we run Docker? We'll find that we don't have permission to the socket. You need to have, you have to be in the Docker group. I don't want to run things as root, so I'm going to add myself, the Ubuntu user, to the Docker group. Okay, there you go. So now we can do Docker PS, and we can see we have no images, we have no containers running because, well, we just launched this instance. So you can get, this is just Docker usage. So you can attach containers, build containers, commit them, kill them, load. There's a way to actually load and save images as well as import and export. So there's some facility for actually importing legacy systems. So if you have just a hard drive that you want to import and make a Docker container, you can do it. And this is getting Docker load. So this is just, you can get information on Docker itself. So Docker has we're using the AFS storage driver, the execution driver, which is native. I should also mention in Docker 0.9, we added a thing called libcontainer. And libcontainer is a Go library for managing Linux namespaces without using LXC. So Docker no longer relies on LXC, and it provides us more capability for doing some of these advanced features of namespaces that libvirt may not necessarily provide us. All right, so we can get a list of the images that are on our machine. So we have a BusyBox image. And we can run that BusyBox image. So we're just going to do docker run -t-i, which gives us a terminal, which is interactive. The image is BusyBox, and we're running bin sh. And once we have sh, of course, we can run things in it, like ls. I may have cut that demo short. So what we're going to do here is we're going to clone a repository that I made. And this is basically going to build Samba. So let's see here. So I have a base image for Samba. And there's a file here, docker smb user. This is what we're going to add into the image. So we do from Ubuntu latest. I'm the maintainer. We're going to install some packages in there. I guess we need extras or something. We need Universe. We're going to install a couple packages. We install Samba. And then we build it. So it's as simple as running docker build. And you can do, so I'm going to tag it and then give it the local directory. Because there's a, basically, you have to tell it where the Docker file is. So you give it a directory. So it's a current directory. And it's going to download Ubuntu from the internet. It'll do this automatically. So if you have a base image that you're using and it's in the registry, it will download it. If it's already local, it's just going to use what you already have. And if you ever want to update it, you do a Docker pull, and that will always fetch the latest image. Okay. So the nice thing is, of course, is as slow and painful as this is to watch, you only have to do this once every time you build the image, right? So you don't have to, every time you run a test, you don't have to do this. And you don't have to build your own imaging tools or one-off scripts that build these images for you so you can run them in VMs. And it provides us right through the Docker file, which is almost like a recipe. So just like you have a recipe for Chef or Puppet, you have a recipe for building these images. All right. I'm losing my patience here waiting for this, so I'm gonna skip the next slide. All right, so what we can do is once it builds finally, we can run it. And let's see. All right, so I'm gonna show you how we can create files in here and use the copy and write. So we just created a file, ABC. And at the very top there, you can see this file called ABC. And what we're going to do is we're going to we're going to leave this container, and the container will no longer be running. Right? There's no longer, the process ended, thus the container is not running. And when we relaunch a container, you see the file's not there because we're using copy and write. Everything that we did before has been discarded. Now you can get it back if you want to. The state of that container is around. The files have been committed to disk, but they're not committed to the image. So we could actually promote that image if we wanted to, which we're doing right here. So we can commit that image. And what we did is we just created a file called XYZ. And now what will happen is Samba XYZ will now be a new image that was committed that contains that XYZ file. So if you want to basically commit it and then launch new containers off of that, we have that file in there. OK. And this is just a small example of using PyPI. And what we can do is, this actually tried to even use virtual env, which is for Python. And unfortunately, it was a little fast. But what it will do is you can download your pip requirements and all your PyPI requirements and have something a little bit above and beyond just having, say, Docker requirements files, right? It's almost like using Docker in this way provides something almost similar to WAR files for Python, as opposed to just having as opposed to just having a requirements file that you have to manually install. And it provides a way to ship that code and ship everything together. So, oh, that was actually the end. Oh. So it's time for questions.
Yeah, can you talk briefly a little bit about like using boot for Docker and OS 10, the limitations?
Sure. So for those of you that are Mac users, there is a Mac support for Docker. And what it is effectively a Docker client. So the Docker CLI program talks to a Docker daemon. So the Docker daemon sits on your host and allows you to actually do all this Docker magic. But the Docker CLI tool doesn't actually do any of this work. It only talks to the Docker daemon. So on macOS, you can use that CLI tool to talk to a Docker daemon that happens to run, say, inside of a VM. So we had this official macOS support where there's a project called boot to Docker. And boot to Docker is a lightweight VM that has Docker running inside of it. So you can use, well, boot to Docker actually just uses VirtualBox directly. It doesn't use Vagrant. It just uses VirtualBox. And it's a VirtualBox VM that runs and has Docker inside of it. And when you run Docker on your, let's say, your Mac, you can then control that Docker instance inside of that container. Now, there are some limitations of using Docker this way. Primarily, things like, I think doing builds, the way that you add files, the way you, like mounting, so Docker has this ability to do bind mounts. So when you do bind mounts, it's going to do bind mounts from the host. So you have to just remember that everything you're doing with the boot to Docker is existing inside of that VM. So when you do something like a bind mount to share resources from the host, it's not the host where your host is not the Mac where you're running your client agent, right? The host is the physical VM where that you're controlling. So you would have to actually, let's say, share resources into the VirtualBox VM, potentially from your Mac, and then use Docker to share resources from within the VM into the containers, if that makes sense. Back there? There's a... Oh.
What are the downsides?
Downsides
to
of
using Docker?
Versus what?
Versus not using it.
So
versus maybe a traditional hypervisor base.
Right. Yeah, because versus VMs, VMs are slower, but they have tighter isolation. Where one of the advantages of Docker is that there's looser isolation between the processes, where you'll be able to potentially share some of these namespaces. So instead of being able to say, like right now, every container gets its own network interface or virtual or IP address. But you could potentially say, well, I want multiple containers to share an IP address, and it's not something I'm not something I would say you can do today necessarily, okay? But eventually, you'll be able to use these namespaces, I think, to loosen the isolation between containers. So that's one of the advantages, but the flip side of it is that you have this looser isolation, thus something like a kernel exploit that exists in a container is going to affect the host and all the other containers. So there's an easier breakout scenario than versus, say, a VM. But on the other hand, a VM generally comes with a full set of processes that Docker containers don't. So there may be less exposure because you're not running, say, SSH or these other processes inside of there that could be exploited. So there's definitely a trade-off in security. Let's see. I'm sure there's a number of examples people can come up with, but I don't see a lot of negatives about it, so it's hard for me to give you more. We have a
if my application is trying to go over SSL Open VPN or a VPC to go to say S3 or something, can I do that?
Sorry, could you repeat that?
If my application is accessing a protected resource through a VPN, like a S3 bucket with the
Right, so what you want to do generally with your containers is first of all, you could set up your host to, let's say, do VPN into another, say into VPC. You could like connect to VPC through, say, your host. You could have your container potentially do it. There are some technologies, some VPN technologies that you won't have the privileges to do inside of a container. And in those cases, you may not be able to, like let's say you need to load a kernel module to connect to a VPN. You're not going to be able to do that from a container. Now, you might be able to load the kernel module from the host and use it in some cases. But sometimes you don't have the control over the networking stack enough in the container to do all VPN technologies. And you can do this from the host. Certain other technologies you can, and there's all sorts of tunneling and VPN things you can do inside a container. And unfortunately, it's a case-by-case basis on what's going to work or not. Back there? Oh yeah, go ahead.
So one of the problems you described in the beginning is that you have a couple developers and they all sort of customize their own development environment. And so you're giving them this Docker container. They're ultimately going to make changes to that container. How do you manage a number of developers working together, all making changes to their Docker containers?
Right. So ideally, you instill a cultural process where people modify the Docker file, and they submit a pull request to the Docker file, as opposed to making localized changes inside their image and committing those into images, ideally. And sure, you're right, there's always going to be sprawl and developers that do what they want to. But at some point, I think it has to become cultural.
Excuse me, I actually have two questions. If you want to answer just one, that's fine. The first one is if there's any plans to build orchestration capabilities into Docker itself. And the second is that in terms of security updates, just apt-get updates, how do you usually handle that with a container where every layer is cached? Do you just keep tacking on update commands to the end? Or what?
So let me answer the second one first. There's two ways you can do this. You can either do a new build. So you get a fresh build that has all the, let's say you do an apt-get install and it includes all this, it does apt-get update and apt-get install. It will have the latest requirements and pull in all the latest changes that you need. So that's one solution. The other way is to use your current image, commit it, or perhaps it's already committed as an image, right, as a base image, or it's tagged as an image rather, and then you create a new Docker file that uses that as a base. So you can say, well, version 1.0 of my product is this Docker container, and version 1.1 is this new Docker file that says from my app :1.0, and then apt-get update, apt-get update, apt-get upgrade, right? And that could literally be, your 1.1 product if you wanted it to be. So you can manage updates that way. You can also potentially do it manually and manually commit images, but I don't recommend it. I always tell people it's better to use Docker files because they're more transparent, they're more documented, and you know what happened and what the delta is between the images. As for the first question about orchestration, we recognize that it's something that people want, and I'm not going to commit to what we will or won't do, but I see that as being something useful that we may work on, not necessarily as part of Docker itself, but as a Docker ecosystem solution, right? So there are things like Sky DNS, for instance, which isn't Docker, but is related to Docker and is useful to the Docker community. And we've actually been working on a number of things that are going to be, say, other Docker containers that can link to your existing Docker containers to provide things like orchestration or various services. But it's a little early to say specifics of something that doesn't exist. Okay. Do you have a question still in the front? Oh, sorry.
Does Docker have any concepts for high availability built in, or is the idea that the apps that it supports should have high availability through horizontal scaling?
I would say you should use horizontal scaling. I see Docker as strongly advocating the cattle approach in the pets versus cattle diagram. So for those that aren't aware, there's this idea of scaling and cloud where you can have these pets, right? And you pet them and you care for them and you make Wikipedia pages about them. And then there's cattle, right? Nobody makes Wikipedia pages about individual cattle. There's too many, and nobody cares, right? And that's kind of where Docker fits in, is you make them cattle, and ideally you would make one image from one application, you just deploy many of them and you horizontally scale it. Get in front here. He's been raising his hand since the beginning.
No, I was just wondering, are there any businesses or projects using Docker that you're, like, in a way that you're excited about or that was unexpected for you?
Almost every case of people using Docker, almost seems exciting to me. I do hear about a lot of, exciting projects, and there's some really big companies that, have spoken to us about Docker and either how they're using it already or how they plan to use it. That's exciting. But a lot of the first people using Docker are definitely looking at it for their CI and their development tools, because a lot of developers are interested in using it and using it on their workstations. But then that's kind of pushing off to doing CI and then eventually production use cases. And I think a lot of the most exciting stuff right now is seeing people actually successfully getting through the whole spectrum. And getting off of just doing it on their laptops, right? And actually starting to use it in CI, and then those few people that manage to get all three of them is exciting for me. All right, any other questions? All right, well, thank you very much.